I want you to do something for me right now, wherever you are. Just take your hand and place it flat against the device you're using to listen to this deep dive.
Yeah, whether it's, the back of your smartphone or the bottom of your laptop.
Right, or even like the casing of your smart speaker. You feel that faint, steady warmth. That is waste heat.
It's the physical, completely unavoidable byproduct of computation.
Exactly. Every single time you ask an AI a question, every time an algorithm like curates your feed or generates an image, billions of microscopic transistors are flipping on and off.
And generating that exact heat.
Yeah. Now, I want you to take that gentle warmth against your palm and scale it up in your mind. Multiply it by 1,000, now 1,000,000, now a trillion.
Which is, it forces a complete failure of human intuition when you scale it to that degree.
Right.
Yeah, we're no longer talking about a warm piece of metal on your desk. We are talking about, industrial scale, localized climate change occurring inside these massive concrete warehouses all over the planet.
It's terrifying, honestly.
It is. The infrastructure required to manage that heat and power is literally reshaping the global economy right now.
Well, welcome to this deep dive. Today, we are immersing ourselves in a highly detailed, deeply technical manifesto. It was published on June 11th, 2026 on the Netizen blog.
And the title of the piece is Land-Based Compute, Low Earth Orbit Compute.
The premise here is fascinating because it forces us to, confront a physical reality we usually try to ignore with airy metaphors.
Right, like we talk about data living in the cloud, but
the cloud is incredibly heavy.
exactly. The cloud is forged from thousands of tons of structural steel, advanced silicon, miles of copper wiring, and millions of gallons of industrial cooling water.
Okay, let's unpack this. Our mission today is to explore the impending age of abundance driven by artificial intelligence, but more importantly, to dissect the massive physical bottleneck standing in its way.
Which is really the core question. Where on Earth do we physically put all the computers required to run this future?
Yeah, and how do we power them without catastrophically melting the grid? Because the source material sets up an incredible showdown.
We're comparing the massive terrestrial data centers we rely on today against a prospect that sounds, frankly, absurd at first glance.
Putting AI data centers in low Earth orbit, it sounds like science fiction.
It really does. But I am going to connect the dots for you between raw terrestrial economics, the intricacies of orbital physics, and the sheer explosive power of modern rocketry.
Because this isn't an abstract engineering hypothetical.
Not at all. The solution to this bottleneck will determine the cost, the availability, and the geopolitical control of the very intelligence that will run the future economy.
So let's start with the immediate crisis on the ground, the terrestrial gridlock. The core argument the Netizen piece makes is that Earth-based computing is currently winning.
Yeah, it wins on pure cost, it wins on the sheer density of servers you can pack into a single building, and obviously maintainability.
Right. If a server rack goes down, a technician just walks down a literal aisle, unplugs a blade, and swaps it out.
Yeah. Exactly. Super easy. But this model has hit a massive, impenetrable physical wall. And that wall is energy throughput.
We have to look at the power draw delta between traditional computing and AI workloads.
Yeah, for years, a standard server rack running typical web hosting or database management would draw about 10 to 15 kilowatts of power.
And the entire architecture of the modern data center was engineered around that 10 to 15 kilowatt assumption, right?
Right. The backup generators, the gauge of the wiring, the airflow dynamics, all it.
And the AI boom just completely shattered that assumption.
Utterly shattered it. We shifted from traditional CPU processing to massive parallel GPU clusters required to train large language models.
And the source points out that an AI rack isn't pulling 10 kilowatts, it's pulling anywhere from 50 to 150 plus kilowatts in the exact same physical footprint.
The density is staggering, which is why the infrastructure is buckling. You're trying to force a tenfold increase in power density into facilities that were simply not designed to handle it.
Wow. And when we zoom out from the individual rack to the global scale, the numbers become difficult to parse.
They do. In 2024, global data center electricity use was around 415 terawatt hours.
Which is what, roughly 1.5% of the total electricity generated by humanity?
Yeah, exactly, 1.5%. And driven by AI, this number is projected to more than double by 2030.
We are looking at McKinsey estimates suggesting a $6.7 trillion investment required to scale global AI compute infrastructure by the end of the decade.
6.7 trillion. It's hard to even wrap your head around that number.
And all that money is frantically scouring the globe for a place to plug in. The Netizen blog breaks down the geography of power in a way that highlights how desperate the hyperscalers are.
Yeah, they aren't just looking for land. They are hunting for the absolute cheapest, most abundant electricity on the planet.
Because electricity represents the vast majority of the total cost of ownership over the lifespan of these workloads.
Exactly. The economics of power are dictating the geography of our future intelligence. The author actually segments the world into distinct cost tiers.
Right. At the bottom, the lowest cost regions, you have subsidized environments like the Middle East. Qatar is specifically highlighted,
Yeah, offering power at 3 to 7 cents per kilowatt hour.
which is heavily subsidized by the state to attract the infrastructure, right? It's a strategic geopolitical play, not just a free market rate.
Absolutely. It is treating compute as a sovereign asset.
Mhm.
Then you move into the industrial sweet spots, running 5 to 10 cents per kilowatt hour.
And this includes places like Vietnam, parts of China and India, and crucially, specific states in the U.S.
Right. North Dakota, Idaho, and Texas are massive players here.
Texas is a prime example because it sits on abundant natural gas reserves and massive renewable energy potential, right?
Yeah, combined with a regulatory environment built for rapid industrial expansion.
But then you look at the other side of the spectrum, the high-cost regions that are effectively pricing themselves out of the age of abundance.
Like Europe, specifically Germany and Ireland, where industrial rates are pushing well past 20 cents per kilowatt hour.
California and Hawaii are in the same constrained bucket too, right?
They are. But, the cost of the power is almost a secondary problem to the availability of the power.
Right. It's like trying to plug a stadium's worth of floodlights into a single residential wall outlet.
That is a perfect analogy. Because even if a hyperscaler has the capital to pay 20 cents a kilowatt hour, they run into the physical wall of the grid itself.
The interconnection queue.
Yes. The time it takes for the local utility to approve and physically build the high-voltage transmission lines to a new data center. It's stretching to 4+ years in many major markets.
4 years. 4 years in the AI industry is an entire geologic era.
A GPU cluster is practically obsolete by the time the utility company finishes wiring the building.
That delay is forcing companies into incredibly extreme measures. They are effectively abandoning the public grid.
The term used in the manifesto is behind-the-meter power. If the grid is 4 years away, you just build your own grid.
So we are seeing data centers co-locating with or directly purchasing gas turbines to operate private power plants.
Yeah, and the source details the shift toward small modular reactors, or SMRs. The hyperscalers are literally exploring localized nuclear power to bypass utility bottlenecks.
Wait, really? Localized nuclear power just for data centers?
Yes. And in Europe, the Middle East, and Africa, they are deploying massive independent renewable microgrids paired with utility-scale battery storage.
Which the text notes can save up to 40% compared to drawing from constrained public grids.
Exactly. But all of that localized power generation brings us right back to the waste heat we started with.
Right. If you pump 100 megawatts of electricity into a building, thermodynamics dictates you are effectively operating a 100-megawatt space heater.
And you have to remove that heat, or the silicon melts. The energy cost of cooling is a massive compounding factor.
The author mentions data centers aim for a power usage effectiveness, or PUE, of 1.1 to 1.2. What does that mean exactly?
It means for every watt of power used for actual computing, you spend an extra 0.1 or 0.2 watts on cooling and facility overhead.
Which sounds highly efficient, until you realize that 10% to 20% overhead on a gigawatt-scale facility is enough power to run a small city.
Right. Dedicated entirely to air conditioning and water evaporation.
And that requires massive water usage in regions that are frequently dealing with drought conditions.
It's a huge problem.
Yeah.
So we have this perfect storm on the ground. Hyperscalers are desperate to build out AI infrastructure to usher in this age of abundance.
But they are blocked by multi-year grid delays, massive local political opposition over water and land use, and the sheer physical limits of power transmission.
Exactly. If the grid is fundamentally maxed out and local communities are pushing back, where do you put the infrastructure?
The friction of the terrestrial model forces us to look in a completely different direction, up.
Yeah. The physics of space offer an incredibly elegant solution to the terrestrial energy crisis.
Because in a properly selected low Earth orbit, the sun never sets. You have access to uninterrupted, blazing 247 solar energy.
And there are no grid interconnection queues, no local zoning boards, and no fresh water required.
It is an environment of theoretically infinite, clean power.
But of course, the immediate reaction from anyone hearing this is that launching data centers into space is absurd.
Right. Historically, the cost of escaping Earth's gravity made this mathematically impossible. You don't bypass a local utility bill by spending billions of dollars on rocket fuel.
But the Netizen manifesto details how the economics of rocketry have fundamentally altered the math over the last few decades.
Okay, to appreciate the paradigm shift, we have to trace the historical cost curve to low Earth orbit. During the era of the NASA space shuttle, what were the costs?
The cost was roughly $54,500 per kilogram. A single launch cost approximately $1.5 billion for a 27,500 kilogram payload.
It was a bespoke artisanal process, meaning launching something the weight of a standard server rack would cost millions of dollars.
Exactly. You couldn't build infrastructure at that price. You could only do bespoke scientific missions.
Then SpaceX introduced the Falcon 9 and the concept of partial reusability. By landing the first stage booster and refurbishing it, the cost plummeted.
Yeah, from $54,500 per kilogram to roughly $2,720 per kilogram.
That is a 20x reduction, a historic deflationary event.
Current effective costs for the Falcon 9 and Falcon Heavy family in 2026 sit between $1,000 and $3,000 per kilogram.
It's an incredible drop, but frankly, at $2,000 a kilogram, it is still way too expensive to launch tens of thousands of tons of heavy compute infrastructure.
Right, but the source outlines the transition happening right now with Starship. We're moving to a fully reusable launch vehicle targeting 100 to 150 metric tons per payload.
And the near-term goals are $50 to $200 per kilogram, with analysts viewing $100 to $500 per kilogram as highly realistic in this 2026 to 2030 window.
That is the inflection point. Moving from $50,000 to $500 is a 2 orders of magnitude reduction. It completely rewrites the rules of what is economically permissible in orbit.
You know, I think it's important to push back on a very common misconception here. Most people think rocket fuel is the reason space is expensive. Is that true?
What's fascinating here is that the propellant is almost mathematically irrelevant to the final price.
Wait, really? The fuel isn't the expensive part?
No. The massive drops in launch costs have virtually nothing to do with the price of liquid oxygen or methane. The revolution is entirely about operations and manufacturing.
So it's about how the rockets are handled, not what they burn.
Think about commercial aviation. If an airline flew a Boeing 737 across the Atlantic and then deliberately crashed it into the ocean upon arrival, a single ticket would cost millions.
Oh, wow. Yeah, the jet fuel is a fraction of the cost. The expense is the destruction of a highly complex machine.
Exactly. Full reusability means amortizing the manufacturing cost of the vehicle across hundreds of flights.
You are dividing the capex of the rocket by its lifespan, just like a terrestrial data center.
Furthermore, the manufacturing process itself has fundamentally changed. The industry moved away from exotic, incredibly expensive aerospace carbon composites.
And towards mass manufacturing with stainless steel, right?
Yeah. They applied Henry Ford-style assembly line techniques to complex components like the Raptor engines. This vertical integration strips out the massive markups of traditional defense contracting.
You combine mass manufacturing with airplane-like rapid turnaround, and the cost of getting mass to orbit just collapses.
It does.
So getting to space is rapidly becoming cheap. The rockets are effectively becoming cargo trains.
Right.
The logical conclusion most people jump to is that we just pack a Starship full of dense AI servers, launch them, deploy some solar panels, and turn them on.
Yeah, it seems so simple.
And intuitively, you'd think the best part of putting a data center in space is that space is freezing cold.
Right.
We leave the massive water cooling towers on Earth and just let the icy vacuum of space show the hardware.
It is a common, intuitive assumption, but the reality of thermal dynamics in a vacuum turns that completely upside down.
Really?
Yeah. Space is not a refrigerator, space is a thermos.
Okay, this is where we hit the real physical bottleneck. Let's dig into the thermal mechanics, because the Netizen piece explicitly targets this myth. If space isn't cold, how do we keep these incredibly dense AI chips from melting into slag?
We have to look at the fundamental physics of heat transfer. On Earth, if you have an overheating component, you blow air over a copper heatsink.
Right, the air molecules absorb the thermal energy and carry it away. That is convection.
Or, alternatively, the heat transfers directly into the physical structure it's resting on, which is conduction. Both require a physical medium.
But in the vacuum of low Earth orbit, there is no air. There is no water. There is zero physical medium to carry the heat away.
Exactly. Convection and conduction are mathematically zero. The only remaining method of heat transfer is thermal radiation.
So the object must emit its waste heat away as infrared light into the void.
Yes, and relying entirely on thermal radiation is catastrophically inefficient at the relatively low temperatures required by delicate electronics.
Okay, let me get this straight. Running an AI data center in space is like trying to cool down an overheating gaming laptop while it's wrapped in a vacuum-sealed emergency blanket. And you can only cool it down by letting it sweat out infrared light.
That is exactly what it's like. It's a nightmare. The author of the manifesto points to the Stefan Boltzmann law to explain the brutality of this problem.
The Stefan Boltzmann law.
Okay. Yeah, this law dictates that the rate at which an object radiates heat scales to the fourth power of its absolute temperature.
It is known in engineering circles as the T to the fourth problem.
Yeah,
right?
exactly. T to the fourth, which means if you slightly increase the temperature of the object, its ability to radiate heat away increases exponentially.
So if you have an object operating at 1,000 degrees, like the nozzle of a rocket engine, it radiates heat away fiercely. It's highly efficient.
But AI chips cannot operate at 1,000 degrees.
Right. The text notes they must be maintained strictly between 20 and 80 degrees Celsius to avoid massive current leakage and catastrophic failure.
And because you are physically restricted to these low temperatures, the T to the fourth equation works entirely against you.
Let's put the specific numbers from the manifesto to this. It's one thing to say it's inefficient. It's another to see the actual physical footprint required.
Okay, at roughly 20 degrees Celsius, a highly optimized two-sided radiator panel radiating into deep space can only reject about 600 to 800 watts of heat per square meter.
Now recall the massive power demands we discussed earlier. A single AI cluster might draw 1 megawatt. Therefore, it generates 1 megawatt of waste heat that must be rejected.
Right, so if a square meter can only shed roughly 800 watts, and you had to shed 1,000,000 watts,
Yeah.
you need between 1,200 and 1,600 square meters of radiators just to cool a single megawatt.
That is the size of a professional hockey rink of solid metal radiators deployed in orbit just for 1 megawatt of compute.
And hyperscalers are building gigawatt-scale facilities right now on Earth.
Wow. To scale to a gigawatt in orbit, you are talking about radiator structures that are miles across.
And the physics get even more punishing because you are in low Earth orbit, which introduces severe environmental complications.
Right. You aren't just floating in deep, empty space. You are circling a massive planet.
First, you have thermal cycling. A satellite in LEO orbits the Earth roughly every 90 minutes.
That means every 45 minutes, the data center plunges into the freezing shadow of the Earth.
And 45 minutes later, it emerges into the unfiltered, blistering glare of the sun, experiencing a solar flux of over 1,300 watts per square meter.
Your radiators are constantly being baked and then frozen, expanding and contracting every hour and a half. That stresses materials to the breaking point.
Furthermore, they must deal with Earth's albedo.
The albedo.
Yeah, the sunlight bouncing off the oceans and clouds, as well as the infrared heat constantly radiating from the Earth itself.
So your massive hockey rink radiators need a clear, unobstructed view of deep, cold space to function properly.
But the Earth is dominating half your field of view, and the massive solar arrays required to power the data center are taking up the other half.
And those solar arrays generate their own heat that needs managing. It's an endless loop.
The source also highlights a subtler problem with microgravity.
Oh, right, because on Earth, if a fluid heats up, it becomes less dense and naturally rises.
Exactly, creating convection currents that help move the heat away from the processor.
But in microgravity, hot water just sits there. You have to mechanically force the fluid to circulate.
Which requires heavy mechanical pumps, complex fluid loops, and multiple points of failure.
All of this cooling infrastructure, the miles of heat pipes, the pumps, the radiator panels themselves, they're all made of metal. They are incredibly heavy.
And as we established, mass is the enemy of orbital economics.
The author provides the International Space Station as a benchmark, right? The ISS External Active Thermal Control System.
Yes. The ISS rejects roughly 70 kilowatts of heat. To manage that relatively small load, it uses radiator wings that weigh about 7 metric tons.
7 tons for just 70 kilowatts. If we naively scale that heritage technology up to our 1 megawatt AI data center, we are looking at 100 metric tons of radiators alone.
And the actual silicon computing hardware might only weigh 10 tons.
You are launching an order of magnitude more weight in cooling plumbing than you are in actual processors.
It is a staggering penalty. The entire economic model collapses if you have to pay launch costs for 100 tons of deadweight aluminum for every megawatt.
How is the industry attempting to engineer their way out of this? Because clearly they are trying.
They are aggressively targeting the aerial density of the radiators. Current space radiators weigh between 5 and 12 kilograms per square meter.
And the goal is to use advanced composites and embedded capillary heat pipes to drive that down to under 3 to 5 kilograms per square meter.
Exactly. They are also heavily researching mechanically pumped fluid loops using ammonia and phase change materials.
Oh, phase change materials. Those act like a thermal battery, right?
Yeah. They absorb the massive heat spikes when the satellite is in direct sunlight by melting, and then release that heat into deep space when the satellite passes into the Earth's shadow.
It buffers the thermal load, but the most radical concept discussed in the text is the liquid droplet radiator.
This sounds like absolute science fiction, but it elegantly addresses the mass problem.
How does it work?
Instead of piping hot ammonia through heavy metal panels, a liquid droplet radiator sprays the hot fluid directly into the vacuum of space as a fine mist.
Wait, just sprays it out into space?
Yes. These microscopic droplets radiate their heat into the void incredibly efficiently because they have massive surface area and zero structural mass.
And then what?
Then, a collector at the opposite end catches the cool droplets and pumps them back into the data center's heat exchangers.
Wow. It completely eliminates the massive metal panels. But the fluid dynamics of containing a mist of hot liquid in a vacuum while hurtling around the Earth at 17,000 miles per hour.
And dealing with orbital debris that could disrupt the spray. It's an engineering nightmare.
It is non-trivial, to say the least. The vapor pressure of the fluid has to be perfectly calibrated so it doesn't instantly boil away in the vacuum.
Right. But we are seeing companies like StarCloud and Orbit AI actively running tests in small satellites right now.
Validating these thermal architectures using multi-layer insulation, high emissivity paints, and even modular swarm concepts.
Yeah, instead of one massive, vulnerable radiator, you distribute the heat load across a linked fleet of smaller, independent satellite modules.
All of these thermal innovations are desperately trying to cheat the T to the fourth problem, because we are looking at a direct, high-stakes tug of war.
On one side, you have the massive physical mass of the cooling and solar infrastructure. On the other side, you have the rapidly falling cost of launching that mass on a starship.
Which brings us to the economic parity point. This is where the physics and the business models collide.
There is a very specific mathematical threshold where the massive upfront cost of launching all this heavy orbital infrastructure becomes cheaper than staying on Earth.
Right, cheaper than paying for land, water, and grid electricity over the lifespan of the hardware. The Netizen analysis breaks this down into a total cost of ownership, or TCO, calculation.
Let's look at the two sides of the ledger. On Earth, your ongoing operational expenses are brutal.
Depending on your location, electricity alone is costing between $570 and $3,000 per kilowatt per year.
When you stretch that over the 5 and 10-year lifespan of a facility, the energy bill completely dwarfs the cost of the building and the servers.
But in orbit, the economic structure is entirely inverted. You have effectively zero ongoing operational expenses.
Your power is coming from a fusion reactor 93 million miles away. Your cooling doesn't require a monthly water bill or environmental permitting.
However, you pay for all of that power and cooling entirely upfront via the launch mass.
Exactly. You're prepaying for a decade of electricity by buying the rocket flights to lift the heavy solar panels and radiators.
The text estimates that a typical orbital system requires 20 to 60 kilograms of total mass for every single kilowatt of compute power it provides.
And the optimistic near-term engineering targets are aiming for 30 to 40 kilograms per kilowatt.
So when does the math cross over? When does space win?
Well, at current Falcon 9 launch prices of $2,000 to $3,500 per kilogram, orbital compute is not competitive for bulk processing.
It is roughly 3 times more expensive than terrestrial options, remaining a niche application for highly specialized or secure workloads.
But here's where it gets really interesting.
Oh.
The consensus across multiple independent analyses, including Google's Project Suncatcher and various techno-economic models, points to a specific inflection window,
Which is?
$200 to $500 per kilogram to low Earth orbit.
And recall that Starship's realistic near-term target is exactly that, $100 to $500 per kilogram. We are staring right at the threshold.
At $500 per kilogram, the models show a highly competitive levelized cost of energy. We see payback periods of 3 to 4 years for high-utilization AI nodes.
And if launch costs drop below $200 per kilogram, launch mass ceases to be the dominant economic barrier. Orbital compute achieves absolute parity on a per kilowatt-year basis with terrestrial data centers.
But this isn't a static equation. It's a dynamic race between two constantly moving targets.
Right.
If we connect this to the bigger picture, the sensitivities of this model are fascinating. What happens if the terrestrial side of the equation gets worse?
Like if governments implement heavy carbon taxes on data centers or if fresh water becomes severely restricted.
Or if the grid interconnection delays stretch from 4 years to 7 years, terrestrial power becomes vastly more expensive.
In that scenario, orbital compute becomes economically viable much earlier, even at higher launch prices.
And conversely, what if the space hardware leapfrogs current estimates?
Like if engineers perfect advanced thin film solar arrays that unroll like massive sheets of plastic wrap, generating high power at a fraction of the weight.
Exactly. Or if those composite radiators successfully drop below 5 kilograms per square meter.
Then the system mass per kilowatt plummets. Instead of needing 40 kilograms of infrastructure per kilowatt, you might only need 15.
Suddenly, you don't need to wait for a $200 per kilogram launch cost. You achieve parity at $800 or $1,000 per kilogram.
This creates a massive demand pull. The hyperscalers have trillions of dollars tied up in unmet AI demand.
If they are blocked on Earth, they will inevitably pour billions into subsidizing lighter space hardware and faster rocket cadences to force that parity point to arrive.
Okay, let's assume we cracked the code. The starships are flying, the thin film solar is deployed, the droplet radiators are perfectly shedding the heat.
We have successfully parked a gigawatt AI data center in low Earth orbit.
It is happily crunching numbers, powered infinitely by the sun. But a supercomputer floating in the dark is completely useless if it can't talk to the user down on the ground.
Oh, absolutely. And you can't exactly run a fiber optic cable to a satellite moving 17,000 miles an hour.
This is the final and arguably most complex hurdle, the networking choke point. On Earth, data centers are hardwired together by massive bundles of subterranean and transoceanic fiber optic glass.
They offer near unlimited bandwidth, zero latency issues, and virtually no interference.
In orbit, you are constrained by massive distances, atmospheric interference, and the brutal physics of orbital dynamics. Beaming petabytes of AI data from orbit is a monumental challenge.
The Netizen piece details the necessary evolution from radio frequency to optical communication.
Historically, satellites have communicated using radio frequency, or RF S-band, X-band, Ku, and Pa-band.
But RF fundamentally tops out at hundreds of megabits per second. Even the incredible Starlink user terminals operate in that megabit range.
Which is perfectly adequate if you are streaming video or browsing the web.
But artificial intelligence operates on a different scale entirely. AI training and inference consume and generate petabytes of data.
Attempting to transfer the weights of a massive neural network over an RS link is mathematically absurd. The spectrum is too congested.
The data density is too low, and there are hard physical limits on how much information a radio wave can carry.
We have to move from radio waves to light, laser communication, free space optical communication.
Yes, operating in the near-infrared spectrum, typically at 1064 or 1550 nanometers.
Because light has a terahertz scale carrier frequency and can be focused into incredibly narrow, intense beams, it offers 100 to 1,000 times higher bandwidth than traditional RF.
The manifesto cites real-world demonstrations of this capability. NASA's T-Baird mission successfully achieved 200 gigabits per second from low Earth orbit down to a ground station.
And Starlink's internal intersatellite laser links currently operate at 100 to 200 gigabits per second.
The industry projection is that tens to hundreds of gigabits per link will become standard, eventually scaling to terabit bandwidth using advanced multiplexing.
But hitting 200 gigabits per second between two satellites in the vacuum of space is one thing. Shooting a laser from space down through the Earth's turbulent atmosphere to a receiver on the ground is a profoundly different engineering challenge.
The interference is massive. The most obvious obstacle is weather.
If a dense cloud cover rolls over your optical ground station, the laser link is severed entirely.
And the atmosphere itself is also highly turbulent, causing a phenomenon known as scintillation.
Scintillation. It is the exact same optical distortion that causes stars to twinkle in the night sky.
Exactly. The differing temperatures and densities of the air constantly bend and distort the laser beam, leading to massive data loss.
To solve that, engineers have to deploy adaptive optics. It's brilliant technology. The receiving mirrors on the ground are attached to microscopic actuators that physically warp and deform the glass hundreds of times a second.
To perfectly counteract the atmospheric distortion in real time.
Yep.
But even with adaptive optics, you still need a redundant global network of ground stations.
Right. If it's cloudy over the primary receiver in New York, the satellite has to instantly retarget its laser to a clear station in Arizona.
And that retargeting brings us to the hardest part of optical communication: pointing, acquisition, and tracking, or PPT.
Because a laser beam is incredibly narrow, you aren't just broadcasting a wide radio signal in the general direction of a continent.
No, you have to precisely aim a laser from a satellite moving 5 miles a second and hit a telescope mirror on the ground thousands of kilometers away.
The blog specifies the requirement as arc-second level precision. One arc-second is 336 of a degree.
To put that in perspective, it is the equivalent of trying to hit a moving dime from a mile away while you yourself are riding on a roller coaster.
That is insane. It requires advanced, highly calibrated gimbals, stabilizing sensors, and fast steering mirrors.
And all of that PP hardware adds mass and consumes power, directly impacting the launch economics we just discussed.
Furthermore, because you are in low Earth orbit, your connectivity window is inherently intermittent. The satellite rises over the horizon, passes overhead, and sets a few minutes later.
You only have a few minutes of direct line of sight to any given ground station.
So you either need hundreds of ground stations worldwide, or you need to build a complex mesh constellation in space, using space-to-space lasers to bounce the data around the globe until it finds a satellite currently stationed over a clear, cloudless downlink.
But even if you perfect the laser links, the adaptive optics, and the mesh network, you still run into a fundamental mathematical wall.
The data volume mismatch. AI simply generates too much raw data.
Yes. Sending all that raw data back to Earth over lasers is like trying to shove a fire hose through a drinking straw. The physics just do not support moving that much bulk mass of data over intermittent connections.
This raises an important question, and it represents the key architectural insight of the entire networking section. If you cannot efficiently move the data to the intelligence, you must move the intelligence to the data.
The ultimate solution to the bandwidth choke point isn't just faster lasers, it is edge AI, or on-orbit processing.
Let's look at how that fundamentally changes the architecture. Take Earth observation, for example.
Currently, a satellite takes massive, high-resolution hyperspectral images of the Earth, generating terabytes of raw pixel data.
It then has to slowly beam all of that raw, heavy data down to Earth over RF links. A data center on the ground then runs an AI model on that imagery to extract a single insight.
Say, counting the number of shipping containers in a specific port to gauge economic activity.
You are transmitting 1,000,000 pixels of raw data just to derive a single integer as the answer. It is incredibly inefficient.
With orbital AI, you invert the entire process. The high-resolution camera takes the picture, but instead of beaming the raw image down, it routes the data directly into the adjacent megawatt AI data center floating right next to it in orbit.
The AI model processes the image natively in space. It identifies the port, counts the containers, and generates a simple text string. Port of Los Angeles, 14,500 containers.
And then it just beams down that one sentence over the laser link.
Wow. You have slashed your bandwidth requirement by orders of magnitude.
You use the massive orbital compute power to process space-generated data at the source, and you only downlink the distilled high-value insights.
This makes the intermittent, challenging laser connections completely viable because you are transmitting kilobytes of results rather than petabytes of raw material.
So if we step back and combine all of these parallel tracks,
The collapsing rocket costs driven by mass manufacturing,
the engineering miracles of deployable radiators and phase-change thermals,
and the deployment of laser-linked on-orbit edge processing. The conclusion of the Netizen Manifesto is undeniable.
we are looking at a fundamentally altered landscape for human infrastructure as we move into the 2030s. The synthesis here is that we are not heading toward an either-or scenario. We are moving toward a highly integrated hybrid future.
Land-based data centers, situated in regions with cheap, abundant natural gas or massive renewable microgrids, will remain the core, heavy-lift infrastructure for the near term.
They will continue to win on raw cost and density where the grid allows.
But the terrestrial grid can only take so much. The water tables can only handle so much evaporation.
Exactly. Therefore, orbital data centers will emerge rapidly as the vital overflow and premium compute tier. They are the ultimate release valve for Earth's physical bottlenecks.
They offer a parallel operational path, access to unlimited clean solar energy, zero terrestrial zoning fights, and total diversification against ground-based risks like local power grid failures, extreme weather events, or draconian regional regulations on AI power consumption.
So what does this all mean for you, the person holding that warm device in your hand right now?
It means that the fundamental physical architecture of the tools you rely on every day is preparing to move off-world.
In a few short years, when you ask your AI assistant a complex query, or when a medical algorithm designs a bespoke protein to cure a disease,
The immense intelligence doing that cognitive work might literally be powered directly by the sun, computing in the icy vacuum of space, and beaming the answer down to your phone via invisible infrared lasers.
the age of abundance won't just be built in concrete warehouses on Earth. It will be built in the sky. And that impending reality leaves us with a profound, final puzzle.
Something the author hints at with the phrase sovereign compute.
If humanity's most vital AI infrastructure, the cognitive engines that will dictate global logistics, financial markets, and medical research, is physically moved off the Earth and into the international borderless void of low Earth orbit, who exactly controls it?
What happens to a nation's sovereignty, its laws, and its security when the ultimate cloud is literally orbiting above the atmosphere, out of reach of any single government's jurisdiction?
It's an incredible question.
That is a staggering thought to end on. Remember the heat of the device in your hand. The effort to manage that heat is quite literally pushing human engineering off the surface of the planet. Thank you for joining us on this deep dive. Keep exploring the edges of the possible.